Okay. Catalysis. This was also mentioned in the video that we watched. So the rate of a chemical reaction can be changed by changing the reactant concentrations or by changing the temperature or doing both. Right? We learned about that. Both of those have limits. You can only increase a concentration to the pure substance. You can't get it any more concentrated than that, right? And temperature, if you heat it up too much, it might be hot enough that the reactants get destroyed, right? Or if this is in your body, you can't have part of your body operating at 200 degrees Fahrenheit and the rest of it at 98.6. So there are limits. A catalyst will increase the rate of reaction. And what makes it a catalyst and not a reactant is that it doesn't get consumed. It doesn't get used up. It participates in the reaction, and then it comes back out. And so it never gets used up. The way it does that is it provides an alternate mechanism. A different way where that slow step is changed to make it faster. So decomposition of ozone looks like this. The uncatalyzed reaction is a single elementary step. So these two react and form two oxygen molecules goodbye to that ozone. So there's a transition state, there's always a transition state, and an activation energy, right? That activation energy is high, and so this rate is slow, which means that the ozone layer does not rapidly decompose into O2 all by itself. It does a little bit, but not very fast. If it was fast, the ozone layer would not exist. Why do we have problems with our ozone layer? Because of catalysis. So chlorine atoms act as a catalyst. They make available another pathway that has a lower activation energy. So instead of having to get over this big hump, we can do these two little humps, and that reaction is going to be much faster. So these steps here involve the chlorine, but they also return the chlorine. So here's the mechanism for the catalytic destruction of ozone. And fluorine can do this too. And this is why, there's all these regulations about chlorofluorocarbons, because they have chlorine and fluorine, and they get up there and they catalyze the destruction of the ozone. So when we add this together, we see that chlorine is a reactant and also a product. So we cancel that guy out. And then here we have ClO being a product, being produced and then destroyed again. And so that's going to cancel out. And so we get our overall reaction. The Cl doesn't show up in the overall reaction. The ClO also does not show up in the reaction. This one is an intermediate, gets created and destroyed. The catalyst is there to start with. It gets destroyed and recreated. So the chlorine doesn't get used up. So you get, a few chlorine atoms, and they can catalyze a whole bunch of reaction because they don't get used up. You don't need more of them. Where do those chlorine atoms come from? They come from the photodissociation of man-made chlorofluorocarbons. So these get up in the atmosphere, and the radiation from the sun causes them to decompose, and that's where you get the chlorine atoms that are causing a problem. So any questions about that? Catalysts are useful in lots of places. I mean, that was an example of a bad catalyst. We don't want that happening. They're also many good ways that catalysts work. You probably know about catalytic converters, right? We live in California. All gas-powered cars have to have a catalytic converter. Some people have discovered that they can make a nice living by stealing these.
I was like, they're easy to steal, I heard.
Yeah, they're easy to steal, and they have rare metals in them. So the catalyst converter is going to use something like platinum or rhodium or palladium, and this is why they steal them, because they can sell that and make money. And so they have these on a high surface area substrate, and as the exhaust pollutants go over this, they're converted from nitrogen monoxide and carbon monoxide, which are both not good, to nitrogen and carbon dioxide. So nitrogen is the main gas in air, and carbon dioxide, we're all kind of become a little bit sensitive to. But what about my carbon footprint? It's bad to make CO2. CO2 is a natural part of the atmosphere. And so, yes, this is making CO2, but it's not. You don't have these really bad things left. In the process of this, it also promotes the combustion of fuel fragments. So when the fuel burns, when hydrocarbons burn, in theory, you get carbon dioxide and water being produced. Okay, carbon dioxide can be a little bit problematic, but these are not dangerous things. But it doesn't completely combust. And your gasoline is not just hydrogen and carbon. There's other things in there. And in that process of combustion, you can also have reaction of nitrogen from the air, and that's where you get this stuff being produced. So sometimes part of the fuel will be combusted and we'll have some pieces left. This will promote also the complete combustion of those, because we don't want gases like this coming out of our cars either. Any questions? We talk about homogeneous or heterogeneous catalysis, and this has to do with the physical state of the catalyst and the reactant. So homogeneous means the catalyst is in the same physical state, the same phase as the reactants. So the catalytic destruction of ozone by chlorine, we have here's our chlorine, the catalyst, and here's our ozone. They're both in the gas state. It's homogeneous. Heterogeneous means they're in different states. An example of that is the catalytic converter. Here the catalyst is a solid. The reactants and products are gases. I'm not going to test you on this slide. It's just kind of interesting. So we learned about the homogeneous catalysis of the destruction of ozone. And that's going to happen. Did you know that there's an ozone hole that gets formed over Antarctica and then goes away on an annual basis? It shows up and it goes away. It shows up and it goes away. This is not due to chlorofluorocarbons. The chlorine's evenly distributed. It should affect the ozone layer everywhere, not just over Antarctica. So why is this happening? So the chlorine up there is bad, but it's not all just free chlorine. Sometimes it gets caught up in different substances like ClONO2, and when it's bound up like this, it can't catalyze ozone destruction. So that's why the whole thing isn't gone. The ozone hole over Antarctica has to do with clouds. So polar stratospheric clouds have ice particles. Those ice particles catalyze the release of chlorine from these compounds. In the Antarctic spring, then the sunlight dissociates those chlorine molecules into chlorine atoms, and the chlorine atoms are going to destroy ozone. So this process is going to happen until those clouds melt. So the result is we have an ozone hole that happens every spring and lasts for about 6 to 8 weeks, and then it goes away. Any questions? I'm not an expert on this, but yes? Is it supposed to do that? That's an excellent question. I suppose we have to look at the owner's manual for the Earth. Well, so this is happening. Would it happen if we weren't putting chlorine atoms into the atmosphere? Not much, no, it wouldn't. So this hole is most likely due to human activity.
That's the hole that's healing?
Pardon me?
That's the hole that's healing, right? You band all the aerosols with them.
Okay, so this is different than that hole. I mean, in general, the ozone layer is not as thick as it should be.
There are multiple holes.
Well, I don't know, because I'm a chemist. I do know that this hole appears and then it goes away. And I think the problem overall is a thinning of the ozone layer and not necessarily specific holes. So overall, the ozone layer is thinner than it should be, and that's a problem. But this hole, I think when they first discovered the hole, they were like, oh, you know, it's going to end or something. And then they realized, well, it goes away. And so then they tried to figure out, well, what's going on here? And it turns out it was just the ice in the clouds catalyzing this reaction.
The ozone layer is set to fully heal by like 2050, I think. You band all the aerosols.
Yeah, so they've banned aerosols and different things that are causing a problem and causing ozone destruction, and they can map that and predict what's going to happen. And I'm not up on those things, but that sounds about right. Yeah, it is good. Any other questions? Another example of catalysis, hydrogenation of double bonds. So here we have ethene. There's a double bond between the carbons. And this can react with hydrogen to form ethane. So in this, what happens is a hydrogen is added to this carbon and one to this carbon, and then we don't have a double bond anymore, and now we have 3 hydrogens on each carbon. But that happens pretty slow at normal temperatures. But it can be catalyzed by platinum, palladium, or nickel, and then it happens quickly. So the reason that this is slow is that there's a large activation energy due to the strength of the hydrogen-hydrogen bond. In order for this reaction to occur, the hydrogen-hydrogen bond has to break, and that's the hard part. The catalysis weakens that and makes it easier, so it lowers the hump. So what happens here is we get our gas reactants, and they're going to adsorb, meaning stick to, this solid surface. And then there's diffusion that occurs. And this might seem a little crazy, but these gas molecules stuck onto the solid can move around, and they can run into each other. So the reaction occurs, and then desorption, the gases leave again. And so how does this make it faster? When the hydrogen absorbs to this surface, it weakens that bond and can break it, and then it makes it easier for the reaction to occur. So it takes that slow step and cuts the hill, makes it easier. Any questions? Biological catalysts, these are the really, really interesting ones. Most of the reactions occurring in your body that enable you to survive would be too slow under normal conditions, and you would not be able to survive. Enzymes are biological catalysts, and they're usually large protein molecules. And so we talk about the reactant molecule as being the substrate, and that's going to bind to or stick to a particular part, the active site of the enzyme. And it does that through intermolecular forces like hydrogen bonds and dipole-dipole forces. And what this does is it greatly lowers the activation energy, causing the reaction to speed up. So here we have a general mechanism. We've got the enzyme and the substrate, and they're bonding together, right? So here's the substrate, it comes down here, it attaches, and then the slow rate-limiting step is the enzyme substrate then coming apart into products. So enzymes are cool because they're very specific. This enzyme is only going to catalyze the reaction of that substrate. It's not going to affect other things. Some are more general than others, but they can be extremely specific. One of the reactions that enzymes catalyze in your body is hydrolysis of sucrose. At body temperature, it has a very high activation energy, so it's very, very slow. The enzyme sucrase will catalyze that reaction, and it does so by weakening one of the bonds. So here we've got sucrose, which has two parts, glucose and fructose, and they are attached by a single bond between carbon and oxygen. And for hydrolysis to occur, we have to break that bond. Well, it's a pretty strong bond, it's hard to break. But when we get the sucrose adsorbed to the sucrase enzyme, it causes it to bend and sort of twist and put strain on that bond, which weakens it. So it's bent and weakened, and now it can break more easily, and so the reaction can happen much more quickly. Any questions? So enzymes are what allow your body to control what's happening. You have hormones, and they send out signals, and they control different reactions. And how is all of this stuff controlled? It's controlled by enzymes and catalysts. And they're extremely specific. They just catalyze one reaction. And they can speed up reactions by factors as large as 1 billion. This is not like 2 or 3 times as fast. This is like 1 billion times as fast. Substances that inhibit enzymes or prevent them from working can be highly toxic. Because if you need the hydrolysis of sucrose for your body to function, and you've got something in there that's going to interfere with the enzyme, you can't do that reaction anymore. That's not good for you. If you lock up a single enzyme molecule, that can prevent the reaction of billions of substrate molecules. And so some things are extremely toxic because it just takes a few molecules to mess up the enzymes that are making that important reaction happen. Yay, the end.